Welcome back to another Hyomoto and Julien GML podcast programming extravaganza. I'm Hyomoto,
I'm
and
Julian.
he's Julien. And today we're going to be following on from our last podcast and talking a little bit about caching. I'd like to draw your attention to Julian's fantastic hoodie. He made it specifically for this podcast. You could see it last time, but or you couldn't see it last time, but he was wearing it. So today you'll actually be
Mm.
able to see it. Yeah. So last week we talked about the big O notation and kind of how you can reduce how expensive something is by doing less of it. And today we're going to speak more on that operation side of thing, which is doing stuff can be expensive, but if we can cache the results of something and use it over and over again, that's going to be a lot cheaper. It's a bit like making a entire cake instead of one slice at a time, I suppose, because we used cake analogy last time. So yeah, that's going to be our topic, and we're going to start off uh, with a with a complex problem space. Which that's bright on my monitor, so I apologize. But we're going to talk a little bit about the
My
Fibonacci sequence.
Yeah, I do apologize for my handwriting too. So for anyone who's familiar with the Fibonacci sequence, it's basically a sequence of numbers where the first two elements are defined to be one, and every other element, starting from the third, is the sum of the previous two elements. So it goes like 1, 1, 2, 3, 5, 8, 13, 21, and so on. Now, as you can see, if it's like Fibonacci of n equals Fibonacci of n minus 2 plus Fibonacci of n minus 1, that's called a recursive problem, because every single step takes the result of, well, the function for the step before of that and calculates that again. So the function calls itself, and that's called recursive function. But recursion is a different piece we're not going to talk about today.
And kind of interestingly, this is also a very functional argument. Oops,
Mm.
I was going to go to the next page, but apparently I've failed to do so. Oh, I've made
Oh,
everything
no.
worse. All right, there we go.
And the problem with that is in computing, actually, well, the runtime is pretty much O of 2 to the power of n. It has to do with the golden ratio, but we can approximate it to the 2 of to the power of n. That was a complex sentence, I apologize. And as you can see, to calculate the Fibonacci value of 4, you need the results of the value of 3, of 2, and for those you need the value of 2 and 1 and 0 and 1 and all that stuff. And what you will notice if you observe it well enough, you will notice that when you call it in the computer, well, you will call a function multiple times. So if you call f of 1 to calculate f of 2, and you call f of 1 to calculate f of 3, you will have called the same function 2 times, which is not very efficient because you've already done the math. So why do it again? And well, as Hyomoto said, that concept is called caching. And basically, the idea is you store the result of each function call. And instead of calling the function, you check, for example, in a hash table, which we talked about last time, the value at 1 is something, and you check, is the value at 1 stored? And if it is, perfect, you call it and use it as the value in the function approximation again, instead of calculating it again. So by doing that, you like roughly get runtime of O of n, which is much, much, much faster than O of 2 to the power of n.
Oh yes, and once it's been cached, it should just be an O of one problem as well, correct?
Yes, that is true. That's why it goes up to linear space. Roughly, it's a little more complex than that, but you can approximate it to that values.
Yes, of course. And we wanted to start out with that because the Fibonacci sequence is fairly expensive to compute, but it's also fairly easy to understand. But the most important thing that you can understand there is how the Fibonacci sequence doesn't change either. And so while the fastest option would be to calculate that ahead of time, and yes, this would be a form of caching. It's like pi. We just store some approximation of pi. It's close enough, and we can use that. We don't have to calculate pi from scratch every single time we want to use it. And for the Fibonacci sequence, you could store the Fibonacci sequence, as he said, in a hash table, for example, and you could just look up the value you wanted. But sometimes you do want to do dynamic calculations. Sometimes it's not as obvious, sometimes it's not something you can calculate easily ahead of time. But that doesn't mean that you can't cache the results. I was going to talk a little bit about local caching, which is, let's say that we have our algorithm from last week and we have something that we're doing over and over and over again. In this case, something simple, like maybe we're looking up a value in a table. Like, let's say we're looking up the Fibonacci sequence and we're saying, hey, what was the calculated value of 4? Well, even that can be cached, because that lookup, even if it's pretty fast, if we do it 3 times, it's 3 times slower than it would be if we just did it once. And so we could use a local variable using var in Game Maker Studio to essentially remember that throughout the function. And then by doing so, we reduce the amount of times that we have to do that lookup. And again, it's these might be small values, and when we're optimizing for O, sometimes our optimizations may not be great. But if you consider the cost overall, you are putting in a little bit more room to do that calculation somewhere else. And if it is something expensive, then it may be the difference when we're talking about 3D graphics and such. Like, let's say that you have a parrot that's sitting on a pirate's shoulder, and the pirate is sitting on the deck of the boat, and the boat itself is sitting in the water. And so the boat's moving around, and the pirate's moving around, and the parrot's moving around. And if we had to calculate the value of the boat's position, and then we have to calculate the value of the pirate's position, then we have to calculate the value of the parrot's position. And so we don't want to do that from scratch every single time. If one of those hasn't changed, we don't want to recalculate it, because that's a lot of expensive transforms. And in this case, our operation may have been 01, but at the same time, it was a very expensive operation. And by doing this, we can suddenly reduce it. So when we're talking about, small lookups like global and such, there's still some value even in doing that, in terms of like good coding practices. And honestly, there's another value to doing that, which is if you need to change that lookup later on, or that value, well, you don't have to change it 6 times throughout the function. You can just do it in that one place. I thought Julien had something to put on in the end here.
No, I didn't have anything to put on specifically regarding
you looked
that.
like it. I was like, he has something to say right now. So
Yeah,
that's
I was going to mention something. The problem, the good thing about caching, to start off with, that is when you're doing something billions or even billions of times, caching will save you a lot of calculation time. Even if it's just like, even if it's just like something like small, like reducing the lookup time from 3 times to 1 times. But you need to consider this, for example, the YouTube servers. These get probably billions of requests for videos or likes or whatever per second. And it doesn't make sense for the server to, for example, calculate how many likes the video has every single time. And effectively, it's a little more complex than that. But you can think of like there being tiny servers everywhere, and these store the value of the last seen like,
and it has to remember that you liked it, so you can go unlike it later on, or something like that.
Yeah, exactly.
So if it was recalculating that from scratch every time, that would be ridiculous. Uh-oh. I think Julien is frozen up for some reason.
Good enough. And
we're back.
Yeah, it's like stores the amount of likes every second or something, and then that's good enough, because every second seems like real time, but it's a huge difference from asking for something every second.
You bring up a phenomenal example. However, I'm going to say let's put that on the back burner for just a second, because I definitely want to talk about that. But I figure it's worthwhile to take a look at this real quick, because I want to talk about 2 methods that we can use to cache things in, say, a function. And I think it's very worthwhile to look at this, because I do this a lot, and every time I show people this, they seem to go, oh, wow, I didn't really think about doing it that way. So let's say I
I
have
need
my
static.
function. Yeah, sometimes let's use a glitter pen here for our brackets. So I've got my
Oh,
function
that's
here,
really
and there are two ways to do it. So I have my global lookup. I'm saying like, hey, look up my global index, and I do this. Oh, wow, I don't know how to spell index. It would seem. All right, and I want to do this several times. So the first option that I have is to go var index is equal to global index, and this is the one that I think most people are fairly familiar with. And this is cool because this we've gotten rid of that. Now we can use this index over and over and over again, and as long as it doesn't change, we don't have to recalculate, we don't have to look it up again, and cool. But there's another option that we can do, and I do this quite a bit. But let's say that we have something that is relevant to this function, like our Fibonacci sequence, but maybe not necessarily across the entire program. We can actually set it as a static, and I could say my static table is equal to, and let's say my array here is just 1, 2, 3. And the cool part about this is that this array isn't actually going to be allocated until this function is called. So if this function is never called, this doesn't actually take up any additional memory. But once this function is called, this table is going to remain this way for the rest of the time, ostensibly creating a constant for us to make use of. And this could be really helpful, like if we had that global lookup. Let's say that I have something in my global that I need to look up. Uh, then I can do, again, I could say my global index. And now this only had to be looked up once in the entire program. And now this value can be used infinitely without ever having to do this lookup ever again. Now, you may notice one flaw in that, which is, what if my global index changes? Okay, then this method is not going to be a good method, because once you've set that static, it's going to stay that way until the program ends. But if you have expensive lookups, like sometimes I will have function calls in a table somewhere, and I can use a pattern like this to just look it up once in this function because I know I'm going to reuse it a bunch of times without having to do that lookup more than that one single time. And this can also be used as a sort of way to create constants, as I mentioned in GameMaker Studio, where instead of polluting my global namespace by putting it in as a macro or something like that, I can literally just declare it right here in the function, and it will only be declared once, and it doesn't cost any more than it would otherwise. So those are two ways to kind of cache at a local level within our function. So now let's talk about the cool stuff that Julien was getting into.
Yes. What becomes apparent with this example is caching really only works well with things that don't change frequently. Because the thing with caching is caching itself is expensive. There's no way around that because you still need to calculate and everything else. You need to populate a table, whatever. That requires memory and precious CPU cycle. So if you have something that's changing very frequently, like let's say every frame, and you might cache it, but the point being, if you cache it and then don't use that cached value a lot of times, there's no point in caching. And in the example with the YouTube
Yes, if you
thing,
can't reuse that value, it would be very silly to cache it. That ends up being sort of just a waste.
well, the YouTube thing is that network operations are asynchronous and on multiple threads. So a server does a lot of things at the same time. GameMaker does not do that. And that results in funny behavior, such as potentially if you don't cache values properly and you don't do specific set of operations, it ends up in those things where you have 15 likes but 0 views. And that's because the value was cached and reused, and then the server sends something in before the other server sends something in, and then you get funny things. The thing to remember about caching is you store a value to reuse it, but changing that cached value does not mean everything in your code is changed according to that value. Because the cache value, you can think of it as taking a picture of something. If you change something in the picture, obviously the things in real life won't change because you changed the picture.
Just because I draw a mustache on Julian's face doesn't mean he actually has one in life.
Yeah.
Which I do. As soon as these are over, I spend 9 minutes doing it. Um,
Hmm.
so, on that sort of note, there's an interesting side of caching here. It's not really caching per se, but I do kind of want to bring it up as a side here, which is you brought up the fact that redoing this every frame would be expensive. And something you'd mentioned is it's probably good enough to just do it every second. And while
Mm.
that's not explicitly a function of caching, I think it is at least worth pointing out that you can use both of these features together. You could just check, hey, has it been updated every second? And then if it has, then you recache it. Like you don't have to check this every second. And as far as global caching goes, not global, like I guess I'm going to vaguely call it external caching because we're talking about outside of the actual function itself. Is something that's sometimes called a dirty bit or a dirty flag, and we get into something that's called on-demand caching. The idea is when a room starts, for example, in Game Maker Studio, you might be able to do like something I might do is I iterate over all the tiles in the room and use that to populate my collision data. I only need to do that once when the room starts. But if for some reason that data change, like maybe I loaded in a new scene, like I haven't done this personally, but let's just say I did, then I would need to know, hey, this needs to be recalculated. In that case, I'd probably do it when that change was made. But there are some times when you don't really need to, you don't know when that value is going to be accessed again. And so there's no point in recalculating it until that point comes up. Like just because a value changed, it doesn't necessarily mean that you need to recache everything. This is something that will probably sound really weird to some people, but you're like, I changed something. Why wouldn't I do it immediately? And there's this kind of idea of immediacy a lot of people have when programming where they're like, I need to do it now. I need to do it now. I need to check this now. I need to move that now. I need to collide with this now. And in reality, if we're talking about like, hey, 1 second from now, it may be in that 1 second from now that that value hasn't been checked again. It still needs to be cached and it needs to be correct, but we don't know when the next time it's going to be actually looked at is. In that case, we can use a dirty bit. And the idea of the dirty bit is you have your cached value, but you can then flag that it's dirty. And in that case, next time you go to retrieve the value, you say, "Hey, give me that value." It goes, "Oh, the dirty bit's been set. Okay, recalculate it." And if you have a whole chain of values that rely on that dirty bit, you can essentially go back to each one and say, hey, are you dirty? Okay, then recalculate you. Are you dirty? Recalculate you. And you can also get to this point where you only have to recalculate it as much as you necessarily need. Like, let's say you're doing an RPG and the player's strength changes in the attack calculation. Assuming nothing else changed, you can go back in that calculation. You can be like, okay, recalculate the player's damage based on strength, but I don't have to recalculate the enemy's defense. I don't have to recalculate any status effects that might be affecting things. Those are all going to be the same. But the player's strength, ooh, that changed, so I'm going to recalculate their damage. And you get that nice little subset instead of doing everything. You just do this one little bit of it.
Yes, I'm going to talk about something else because I have a nice way of transitioning, so I'm just going to do it the hard way. Another form of caching is, well, I think it's usually referred to as baking and rendering.
Yes.
But the idea is if, for example, you drop procedural things like a tree, which I did a while ago, which is why it's my example.
It's a good example.
Yeah, I wrote an L tree system, and the idea is you have a set of operations and you draw something based off them. Doing these operations is actually a little bit expensive at times, and doing that every single step is not a good idea. So the thing you do is, you might cache something, but that doesn't make sense. And in GameMaker, there's this neat thing called the surface. And the surface is basically a canvas you can paint on. And well, the idea is that instead of drawing into the scene, so with an object, for example, you draw to the surface, and then you just don't update the surface, and then you draw the surface. So you like draw to your canvas, and then you hang it in your game. It might sound a little abstract, but that's because if you haven't used surfaces, they're maybe a little hard to wrap your head around.
So I get to
But the
do a
idea
little
is,
plug here. Was there's actually a surface object in Fast, which makes this very easy to do. And to piggyback off of Julian's example here, if you had a tree that you wanted to draw, you would create the surface, and then you would say if the surface needs to be updated, then redraw the tree. Otherwise, just draw the surface. And the interesting part about that is you could set it to redraw. Uh, that dirty bit I was talking about, it has one. You set it to true. You say, hey, redraw this. Well, it's not going to redraw it until the next time that it actually gets accessed. And so, again, you end up with this nice little caching where you're not doing expensive drawing operations because, like, let's say the tree could have many changes happen to it. For example, let's say that I have 6 different things that tell that surface to redraw. Well, I'm not redrawing it 6 times. I only redraw it the one time when it finally gets time to use it and it says, okay, I'm dirty. I need to reinitialize this. All right. Sorry to cut you off, but I thought that'd be a nice little add in.
yeah, no, I used the fast surface, so
It's one of my
I
favorite
can
features. I use it all the time.
um, well, again, the idea is you don't want to do a bunch of expensive things when the main advantage of a computer is it doesn't forget things easily.
Not until the power
And
goes out.
well, there's also the problem with the caching. It's that it doesn't forget things, so you end up using a lot of memory, and when you don't have that memory, trying to use that memory is not a good idea.
Sure.
So the trade-off you have to do is between speed and memory, and well, it might not be apparent for one surface, 100 surfaces, but if you end up having, let's say, an array with billions of entries, you might think it's a few numbers, but in reality, it's actually megabytes and if not gigabytes of data, and that is
There's an
not good.
internal struggle between CPU cycles and memory. You use memory to save on the CPU, and you use the CPU to save on memory.
Yeah, it's always a trade-off you have to do, and well, especially in game programming, you can be like, yeah, this is good enough. So, in like the example I gave with YouTube polling every second, for example, in games when you have something like collision data in a fighting game, you will need that to be accurate, and
Yes.
you will not want to have that every second. But if you have something like, let's say, a world building game where you want to change the hitbox. Well, you only have to change the hitbox when the player is near it, and it's good enough if you change it maybe a second after something happens or player builds, and you just make sure that in this second he really can't go into that position, and then you merge everything again. It's
I'm
again, it's a trade-off, and you have to make sure that you don't do unnecessary things, but at the same time, you need to remember that nothing comes without anything like going against it. You can't just save CPU cycles and then have no trade-off in this case.
all
Well,
code has to be run. The
yeah,
so it's an interesting case on like sort of caching. I was gonna talk about like crops and harvest moon or something like that, and I will
oh, yeah,
do that next. But I want to talk about something that doesn't seem game related. Garbage collecting. Game Maker Studio has a couple things in it that aren't typically garbage collected, like surfaces and data structures, sprites, fonts, etc. They have to be cleaned up when you're done with them, or they could potentially cause a memory leak. And Juju has a library that I'm forgetting the name of it right off the top of my head. Do you remember it? It's for clearing surfaces. But
oh,
anyways, it's a similar
mosaic,
problem, but I just built something that was really generic like that, and is kind of an interesting little characteristic. Is let's say you had 10,000 items to uh, look at and potentially clean up. Like you don't want to look at 10,000 items every frame and check if they're ready to be cleaned up or not, because that's a problem where everything is going. But if you think about it, these items that we're looking for are cached. We've cached a list of items that we need to look at and decide whether or not these need to be cleaned up in memory. So what I did was on the frame, on the first frame, there was two lists. I did a two generation garbage cleanup. On the first frame, it would look at everything that had been added that frame to that list and checked if it was still there. If not, it would clean it up. Otherwise, it pushed it into the second list. The second list literally only checked one item every frame, just one item. And the fact of the matter is you might have 10,000 items in there, and sure, that would take 10,000 frames to get through that list, but there's a good chance that you don't necessarily need all those items to be cleaned up immediately, because if they weren't cleaned up on the first frame that they were there, there's a good chance that it can wait a little while. You know, even at 10,000 items, I mean, 10,000 is a bit extreme in this case, but at 10,000 items, you know, it would take a couple seconds before it would get around and check it and clean it up. So it's not really a huge issue overall. And that's kind of the big thing about caching is to bring it back to the Harvest Moon example is let's take something like your crops. Now, every frame you could evaluate whether or not the crops have grown. You know, maybe you want it to do it in real time and have the plant sprout before your very eyes. And, you know, you might be able to do that if you want. But what I would argue is that what happens when you leave the room? Do you still simulate the growing of those plants in the background? And that's a lot of wasted resources for something you can't actually see happening. And so you could cache the last value that had been compared as the time. And when you come back to the room, you could just do one calculation to add the amount to the growth that had taken place between those two times. And that's another example of sort of not only are we deferring our processing to a later date, but we're also going to cache a value that we don't, you know, that we don't want to look up. Or that we don't want to recalculate. Sorry, we don't want to calculate how much growth happened since it first started. We know how much growth happened. So we cache that value. And then we just look at the difference between those two times. And we can say, okay, it grew this much in the intervening time.
Yeah, and this is a perfect example of, well, not exactly caching, I'd say, but more like lazy programming. And
I love my
um,
lazy programming.
yeah, basically, a lazy programmer is a good programmer because if something is good enough, why do it the better way? If it's going to be the same effectively, why simulate the real-time growth of a plant? Because you're not going to see it. It's going to be good enough, and that's kind of the important thing about caching is figure out what is good enough, and if there's something like, imagine it like you having to run down flight of stairs every single time you want to do that operation. If you can figure out a way to not have to run down the stairs every single time, you probably will prefer that over having to run down the flight of stairs every single time.
Instead of having to go get an egg from the refrigerator every time, I just bring the whole egg to me, and then I
Exactly.
can use it when I need it. Yeah, yeah, it's one of my favorite phrases is a lazy programmer is a good programmer, but that does take some time to really understand. The comment does not refer to necessarily taking the easiest approach in terms of how much code you have to write. It speaks more to writing your code in a way that will save you time overall. My follow up to that is always the everything easy is hard and everything hard is easy. So do the hard thing and make things easy on yourself. But perfect is the enemy of good, and the lazy coder knows when perfection is not necessary. Do I need to watch my my plants grow in real time? Maybe, if that's the point of the game, maybe. But even then, you could probably find a lazier way of doing that that still yields the same results. My favorite example of this is actually just square hitboxes. When people first start to program, you see people abandon this pretty quickly because it turns out it doesn't actually feel very good. But pixel perfect collision in with the sprites, usually not actually what you want, because you'll end up getting tripped up on single pixels, or maybe the player dies when a bullet just grazes one follicle of hair on their head, or just something like that. You know, nobody gets mad when an enemy shoots through Mega Man, not unless it's to the point where it's cheap. But everybody likes that thrill of avoiding a hit, and if it can err on the side of the player, they're going to enjoy it. And so you can use an approximation like a square hitbox, and that's going to be close enough. That's going to be good enough to represent the player's hitbox. It allows them to have the skill and the chance of getting hit, but at the same time, we don't have to worry about doing pixel perfect collisions, which is very slow. Fun time.
Yeah, that's a good example too. It isn't exactly caching, but it's a good example of being lazy. And another thing about being lazy usually doesn't mean you kind of said it. It like doesn't mean being easy, but it means having an easy way to code something. And well, when you say make it hard on yourself to make it easy on yourself later on, the point of that is that just because something might seem complicated, it's better to have code that you can use easily and reuse it potentially than to have code that you wrote. It might be fast, it might have been easy to write, but if it isn't easy to reuse or if it isn't easy to read, it's not good code.
Or it's not easy to change. And I can promise you one thing, your code will change. And that's when you'll find out whether or not you took the easy path or the hard path.
Mm.
And so, yeah, caching is one of those things that ends up being, I think a lot of people do it in a way that they don't necessarily think about. You know, when we say var equals something, you know, we are caching, but we aren't always doing it necessarily. We go, oh, I'm doing this so I don't have to do it a bunch more times. Sometimes you just do it. You do it because, you know, to point to the laziness. Hey, it's a lot easier to type var underscore I and just type underscore I a bunch than having to type out this global path that I've written 1,000 times. And yeah, it is. And if that's your reason for doing it that way, hey, that works. But then you have more complex forms of caching, which is essentially when you have something very expensive that you need to do. For example, maybe I need to find all of the weapons that are in the player's inventory. Rather than doing that every single time, I can just do it once, and until the inventory changes, I don't have to do that lookup again. Drawing is a place. I will throw this in here at the end because we'll wrap this one up. But I will say drawing is one of the places where there's a term. It's called overdraw, and it refers to doing excessive amounts of drawing that you don't need to do. And the fact of the matter is like take a background in a game. If it's a static background, like let's just assume that your level was a single frame. It didn't scroll, it didn't move around. You were doing something like joust or balloon fight. Why would you redraw the stage every frame? You don't have to. And back in the days of like the ZX Spectrum and the Commodore 64, they didn't do that. They didn't redraw it every frame. They drew it once and then they just drew the sprites. And if the stage changed, then they drew, you know, they changed the tile. They didn't redraw it. Modern computers can do a lot of stuff very fast. So those level of optimizations we don't tend to think about as much as we used to. But the fact of the matter is that drawing is a place where you can probably cache a lot more than you think you can. And like the HUD, for example, your HUD probably doesn't change except for, say, you know, the health bar. It goes up and down, but the image that's behind it and, you know, the score and stuff like that, it's probably not as dynamic. So you can actually draw out your HUD once onto a surface and then just redraw that every time and only update it when like the score changes or when the health changes. And that's still going to be faster than redrawing that every frame. So there's my hot takeaway for this episode. What do you got, Julien?
Yeah, well, one more thing is you should probably cache in a way that makes sense. I was writing a Sprite Stacking library a while ago. I'm going to continue working on it, but so far it doesn't exist. And the idea is in Sprite Stacking, you draw sprites on top of each other, and then you rotate each individual sprite, and then it produces a fake 3D image. It's a really nice effect, but the problem is that you have to draw every single sprite in the rotation, every single frame. And instead of doing that, you probably want to draw all rotations to a surface and calculate the position based on the angle, and then just draw that part of the surface because that's one draw call as opposed to, let's say, 24. And that's a perfect example of caching. It's just
And if your rotation
something
didn't
that makes it
change,
easier.
you can just do it once and you're done.
Exactly.
Oh yeah. And I remember that library. I'm still looking forward to it because it's awesome. Yeah, anyways, this has been Julien and Hyomoto's GML podcast coding extravaganza 2.0, and I hope you learned something about caching today. I've been Hyomoto,
I've been Julien.
and we'll talk to you next time.